So all those participants who joined lately, this is Professor Digvijay Ronge from Department of Mechanical Engineering. So today we are unfortunate that our speaker, Dr. Kopul, is not available for the talk. So instead of that, we will utilize this time for the practicing of the software. This is a very general example we are taking here. This is a wrench, very familiar product in front of you. Its use is to tighten this bolt. This is a bolt you can see here. And here problem is that the end of the bolt is fixed and it will not rotate. And that way we are applying force on the other end of the wrench, and we have to calculate the maximum stresses generated in that wrench. Okay. So this is a geometry already I have put on our group, which downloaded. In geometry, you have to import the geometry. You have to add the material structural steel. In solid mechanics, you have to add two conditions. One is fixed constraint. So you have to fix this face of the bolt, and you have to apply the boundary load on this top face of the other end. Then you have to do the meshing, the built-in mesh, and then you have to solve the stationary study. So let me know how much stress, maximum stress you are getting in the wrench. So please continue and let me know if you are facing any problem at any point of this model. So I will ask some questions. Have you imported the geometry?
Yes.
Okay. Now add the material. So go to the material library, add structural steel. Completed. Okay, next go to the physics, add solid mechanics. Okay, and next go to the meshing, do the mesh. Go to the meshing, do the mesh. And lastly, select the study, stationary study, and try to solve it. So just solve and tell me what will the value of maximum stress generated, one misses stress generated in the range. Yes, completed. Should I share once again? So I hope you have solved the problem. And in the stress, you have to look for the one misses stress. So you can check here. One misses stress here. Now it is like if you really want to know in percentage or in exact value of maximum stress generated. So for that, you have to go to the derived values. In derived values, you have to select maximum. In maximum, you have to go for volume maximum. In that, you have to select this volume. And in expression, you can select the one misses stress. So here you can go solid mechanics and stress. Yes, here you can go for one misses stress. Okay. And unit you can want or you can, I will select MPa. Okay. Evaluate. So here you see it will evaluate maximum stress generated in megapascal. So it is 374.93. That is the maximum one misses stress generated in the body in this one. Okay. Similarly, if you want to know the maximum stress generated in the bolt, you can select bolt here and it will evaluate. Okay. In bolt, value of this is more. In bolt, what misses stress is higher, that is 482.51 megapascal. Okay. In bolt, higher stress is generated than the range. So let me know if you are getting the same values in range and in bolt.
Sir, can you explain the boundary condition once again?
Okay, so here see solid mechanics, both are solids, fixed constraint. Here they have taken this surface of bolt as fixed. Okay, so it is, you will ask, sir, this is not real. Yes, I also agree with you. Generally what happens, this bolt is inside, and there are threads, and we rotate, and that then the bolt goes inside of that machine or that part. But in this case, they have just fixed this end of the bolt, and there is a wrench which is in contact with this bolt, as you can see. Okay, and then here we have applied a force by hand. Okay, here we'll apply a force in negative z direction so that this will rotate, and they wanted to know the maximum stress generated. Okay, kadi kadi, or sometimes what happens, bolt does not rotate because of some constraint, and due to buckling this part also fails. So it happens sometimes. That is why we have to know that maximum stress generated, is it lower than the its yield strain, or maximum tensile strength. So here it is fixed, and the boundary load we have to apply on this top part. Here only this much part I have applied the load. Okay. Let me know this volume maximum value for range and volume maximum one Mr. stress for this bolt, if you are getting the same values. Completed. So next problem here we have is related to heat sink. We'll solve it. While meshing, I am getting warning message each is shorter than the specified element size for the normal element size. So in that case, you can go for finer mesh. Okay, so go to that mesh above the physics control. We have this finer mesh. With the finer mesh, do the meshing, and your mesh will be more fine. In that case, and that way you can solve it. Okay, sometimes what happens, they have given the maximum element size, minimum element size, and the constraints are different than the these sizes, so that's why you get the this error. Okay, suppose age is 1 mm, but your minimum element size is 2 mm. So that way this error will occur. Yes. Okay, we'll go to the next problem. Shall we go? Yes, shall we? Shall we go to the next problem? Okay. Now see, our next problem is related to the electronic chip cooling. So anyway, tomorrow we have one session. In that session, we are anyway going to learn about this thermal management of battery, thermal management of buildings, processes, etc., etc. But still today we'll take a simple problem, and in that way, your understanding will be more clear. Okay, just let me connect the system. Just wait 2 minutes. Okay, so I'll share once again my screen. So I hope everybody has completed the first problem. Okay, we'll go to the next problem. Create a new file again in the COMSOL software. Again, I will drop that file on our WhatsApp group, so you can continue it. Okay. So once again, I will drop the file here on our WhatsApp group. Okay, so I have dropped the file on our group. Please download that file and follow with me. So this time we'll go together. Okay. Downloaded, everybody? Everybody downloaded? Please download that file which I have dropped on our group, and then we can continue. Just a minute, okay. Yes, participants. Yes, others, have you downloaded the file so that we can continue to our next problem on electronic chip cooling? Rahul, yes, okay. Others? Right. So this is again very important application here, electronic chip cooling. So as you know, most applicable in the data centers. So nowadays, yes, data is stored on clouds, but previously there used to be, or still there are in many companies, we have data centers. So for the cooling of the data centers, this study will be there. So go to the add components, add a 3D component, okay? So that way your geometry part will be activated. Yes, everybody is following with me? So yeah, or am I going fast? Yes, participants? Alok Chaudhary, Brajesh sir, Gulam sir, Pradeep Pawar sir, Sanjay Pawar sir, Ravi Kumar sir, Shahid Tambori sir. Yes. Okay. So download that file. In new file, you go to the add component. In that you add a 3D component. Okay. Now in geometry, right click and then you go for insert sequence. So this is just to save the time. Okay. Otherwise, we can go step by step, create each and every component. But due to time constraint, we'll use this sequence file. So in the download section, you can select that file which I have uploaded on WhatsApp group, open that file, and that way you can see a lot of parts or operations are reflecting on your screen. Just simply click on build all. So that way all these parts will be created. Oh, yes. Okay. So you may be saying, sir, what is this? So I'll just hide the air part. So this is the air domain. Okay, wait, something else not right. So here it is. Yes, yes. Okay. This is the air domain. Why I'm not able to? Okay. Let us go to the transparent. That way you might be able to see what is inside of that. Okay. Yes. So this is a now transparent. So outside is this air domain. Inside of that, you have various electronic components on this chip. So here we have this silicon material, which will generate the heat, on which we have these heat sinks are there. So these are the pin fins. Okay. So pin fins job is to take the heat from this chip and do the cooling. Okay. So this is a silicon chip is there, and we have aluminum fins here, and there will be airflow through this channel. Everybody up to this point completed? Let me know. Take the maximum advantage of this faculty development program, because if you do it on yourself, it might take you several months. But if you just follow this process, your things will be quite swift. Completed up to this point? Yes, participants? Okay, yes. Thank you, Rahul. Now, next we'll add material. So again, I'll go to the add material section. So here it is add material. So first material I will add is air, because that is our cooling medium here. Then built in I'll add air. Okay. Then I'll add aluminum, because we have aluminum feed. So here it is aluminum 3003H18 that I will add. And next I will add silicon, okay, because our chip is of silicon. So I'll add a silicon. Now here one by one I will define. So air is only this domain, okay. Then in aluminum I'll add one by one. So in aluminum, okay, so this outer domain is coming in our way, so I'll just hide it. So this is a hide button. Click and hide this section. Now here you can select the remaining things. Okay, this is your again aluminum pin fins section is there for electronic chip cooling, and the last one is silicon. Silicon will be the bottommost chip. Okay, that is the heat generating element. Everybody completed up to this part? Heat generation, or sorry, material assigning. Then next is our conjugate heat transfer phenomena. So in that, either you can go directly and conjugate. So for that you have to go to fluid flow. No, not the fluid flow, heat transfer. In that you have to select heat transfer in solids and fluid. If you select this way, or you can go to the conjugate heat transfer. If your flow is laminar, okay. If your flow is turbulent, then you have to select turbulent. So I'll select laminar flow, conjugate heat transfer, laminar flow. Is it clear up to this point, participants? Let me know. Then in this section, now I'll define the physics. Okay. So where is my other material? Okay, so I'll reset the hiding so that I'll see the air. Yes. Now in heat transfer solid, here you have to select which. Hello. Yes, sir.
So how you added that heat transfer domain?
Yes, sir.
How you added that heat transfer domain?
So either you can add one by one. So see here, add physics. Either you can go to the heat transfer, add heat transfer solid, then you add heat transfer in fluids, or you can go to this conjugate heat transfer section is there separate. So I hope you are aware of conjugate heat transfer. Conjugate heat transfer means both way heat transfer from solid to fluid as well as from fluid to solid. So that is a conjugate heat transfer. In that if your flow is laminar, click on laminar. So in conjugate, if you select laminar, it will automatically give you both the physics. So that is the beauty of COMSOL software. Both the physics are added as well as their coupling, that is a non-isothermal flow multi-physics part is also added. This is the conjugate heat transfer part. Now in this case, define the solid, which one is solid and which one is fluid. So we already know one is air, so that cannot be it. So in fluid, you have to add the one. So fluid part is this air, solid part is this aluminum and silicon. In laminar again, define the domain. So only this outer domain is fluid flow, otherwise other part is solid. So that will not come into the picture. Now in heat transfer model, only the part is we have to add the heat source. Okay, so I'll add a heat source. What is the heat source here? This silicon chip, and let us add okay, why it is giving, yes, heat rate. So go to the heat rate and add let us say 1 watt. Okay, so 1 watt of heat is generated in this electronic chip, right? So that is the part of heat. Then in liquid or the fluid, you have to add the air inflow and outflow. So in that case, inlet. So let us say inlet is here and air is flowing from this side. Okay. Then we have to define the velocity. So let us define the velocity here. So velocity is let us say very low velocity will give 0.05 meter per second. Okay, so that is the velocity I have given. Define the outlet. So outlet, let us say outlet is here. Okay, so air is coming from right and it is leaving from left. Similarly, if you have to add inflow and outflow in heat transfer also. In a heat transfer, I will add inflow So you have to go to flow conditions. Here you have inflow. So why it is not showing? Yes, inflow. Similarly, inflow. So I hope you are following. I am not being fast. If I am rushing the things, kindly let me know. I'll slow it down. So again, inflow in heat transfer, this is the inflow. आता इथं or here you can add the temperature of the air. Let us say temperature of the air is atmospheric. Let us say it is a 300 Kelvin. Okay. And outflow also you have to define. So remember, in both the physics, you have to define inlet and outlet. Your outflow is this one, right? Okay. Now I'll go to the mesh. I'll select the physics control mesh. So physics control mesh, what it will do basically, for the fluid part, it will create a boundary layer mesh wherever there is a interaction between solid and fluid. Other part in solid, it will just create a regular mesh. Okay, so I'll show you what it means. So here we have this part. Yes, so this is a mesh generated. I'll remove this transparency. This is the mesh generated here in the. So now see here, this is the air domain. You can see the boundary layer is there nearer the walls. So that is the Y plus theory, or we generally keep it to capture the shear stress nearer the walls. So fluid flows against the shear resistance of walls. So velocity is zero nearer the walls, that we all know. To capture that phenomena, we keep the mesh fine there with the help of boundary layers. Okay. And now last part, adding the study. So I'll add a stationary study here. Okay. And then I'll try to solve it complete. So I hope everybody is following me and doing the same. If you have any questions, please ask, and then we'll see the results together. Yes, anybody? Any problem up to this point? You can ask me. So this is still solving. So while solving also, you can check the results. So this is the error. So basically, I'll tell you trick. If it goes below 10 to power minus 3, then your solution is proceeding, or it will, there are chances that it will converge. In next, you have to go to convergence plot. For here, you have to look for temperature and velocity. If it is below 1, then again your chances of convergence are high. If it is much above, like it is 1000 or 10,000, these values are there, then there are less chances of convergence. If value is nearer to 1, or let us say below 100 also, then also you slowly it is solving. It is a conjugate heat transfer. Multi-physics problem takes time. If it is a single physics like laminar flow or just structural steel structural problem, in that case it will solve very fast. But in case of multi-physics, there are two physics, like in this case fluid flow as well as heat transfer, we have to solve simultaneously. So that is why it is taking time. So be patient. Within 5 minutes, I hope it will get solved. So is it also running on your PC? So let me know, participants. Is it running on your PC also? Please follow with me. Just seeing the FDP and it will not help you. You all are faculties, you know better than me, or as like me, that without we write anything, we don't remember. Without doing projects, we don't get the insights or the depth knowledge of that domain. So more you practice, more you expert will become. I am following COMSOL from last 4 years. Somewhere I have reached this level. Okay, so it takes patience and practice for this. Anyway, I'm using this for my UG projects. So all these students who are doing their UG projects under my guidance, I'm using COMSOL in their projects. The MTech or the PhD, also I'm using the COMSOL. Okay. So major difference, who are wondering what to select, ANSYS or COMSOL, let me clarify. COMSOL is very user friendly. All the physics, all these processes by solving the model are reflected on your screen. That is very good advantage of COMSOL. But in case of ANSYS, the advantage is that it is a system software. Like you can model, then you can mesh, and then you can link it with different physics. So if you change some parameters in geometry, and if you solve, so definitely it will be reflected in your solutions in the models. So like big systems are there. In that case, you can go for ANSYS. But if your problem is related to product, simple products or simple physics you want to study, and it is not that much complicated, number of parts are less, interaction is less. In that case, you can go for COMSOL. Yes, COMSOL is also good with complex geometries and multiphysics. But in my opinion, yes, we prefer COMSOL in our college. So it is solving. Let us wait for its solution. Is it also proceeding like this way on your laptop? So it is proceeding. We'll wait. So yes, now you can see the problem is solved in this case. Uh, so you can see the temperatures are reached up to 390 Kelvin because of the heating in this field. We'll create a section, right? We'll create a section, then we can observe. Not velocity, pressure. Okay. So here I will add one plane. So let us add a 3D plot group. Let us say it is a temperature of air we want to see. Temperature of air. Here I will add a surface, not this. I will add a slide. Let us keep it parallel to XZ here, and I'll add just one. Okay, let us just plot. So see here, this is what the cooling looks like in this case. So here, silicon chip will is having heat generation rate of 1 watt. To transfer its heat to this aluminum pin fins, and from these pin fins, this heat will be carried away by the air. I can see the cold air from this part comes into the picture, which is shown by blue. It comes in contact with this hot part and it is carrying away its heat by force convection. So this is an example of force convection. Okay, you can see here this air is traveling and it is also carrying away its heat with it. Okay, everybody got the same thing? Let me know. Others, everybody got the same? Yes. Others? Gulam sir, Rahul sir, yes, Ravi Kumar sir. I've got the same thing. So I've just added a 3D plot group. In that I had a slice. In that I have added XZ plane, one slice only, and then we'll get this temperature distribution in that case. This is a simple problem with electronic chip cooling. You can just model any electronic chip, but you have to know the heat rate in that case, heat flux or heat rate. And then you can model easily with that COMSOL software. Waiting simulation for, okay, so Gulam sir, let me know what results you are getting. Now, what should be the criteria, right? So you can do a parametric analysis with this also. You can change the inlet air temperature. You can change the heat rate here and check the cooling in this case. How to measure the cooling, right? How to measure the cooling? In that case, you can create a transient study and then you can measure the maximum temperature in this tube. Okay, so that way you can continue or you can actually measure how much heat is being transferred. Next thing we can also do in this case, so we'll wait for Gulam sir and we'll check will others simulation to get completed. Yes, has everybody completed their simulation? So let me know. So you can check the maximum temperature in the domain also. So to go for the derived values, you have to go for maximum temperature, or you can go for global evaluation. In that, you can check the maximum temperature, right? So I'll go to the maximum volume maximum. I'll add in the air domain. Let us check what is the maximum temperature. Instead of Kelvin, I'll type degrees Celsius. Okay. So maximum temperature you are getting in the air domain is 113.46. So this is very high temperature, 113.43. This is because we have given the air at room temperature. If you decrease the air temperature, definitely better cooling you will get. And let us check what is the maximum temperature in the aluminum pins. Okay, so I'll duplicate this. Instead of 2, I'll give 2 here. Okay. Here, so in aluminum also, I'm getting a little bit higher temperature, but similar, same as air. Okay. Maximum temperature we are talking about. In case of, let us say, silicon, let us say how much temperature we are getting, evaluate. So silica is temperature is higher, 113.48. You can see here energy balance is achieved. Total heat transferred by this solid, that is been heat gained by this fluid. Okay. That way also you can check. So has everybody solved the problem so that I should know, because that is the motto of this FDP. The participant should get the confidence of using COMSOL. Yes. Participants, Shahid sir, Urmila madam, Ganesh sir, Mananjyoti Kalita sir, Shashikant Mane sir, Rahul Panchal sir. Okay, so with this, we'll stop today. Tomorrow we have a morning session by Dr. Apis. He'll be guiding us related to thermal management of buildings and processes. In the afternoon only, I'll be taking the session related to battery thermal management. Again, very good hot topic in the field of electric vehicles. We'll learn how to model a battery on a lump basis and how to do its cooling. So I expect all of you to join tomorrow with the same gist and with same enthusiasm. Okay. Thank you.
Digvijay sir.
Yes, sir.
Yeah, on behalf of participants, I would like to say thank you to you. You explained that heat domain very nicely. Thank you for having nice presentation. Thank you, sir.
Thank you, sir.